Another question actually I shared with you in the mail, like how should we choose the value of R1 and R2 in case of OTA? Like
When did you share?
I asked that question in that mail just half an hour ago.
Okay, I didn't take this. Sorry.
So the question was like, sir, how should we choose the value of R1 and R2?
Which R1, R2? I mean, in the...
I want to use the OTA as a inverting amplifier.
Okay.
Non-inverting amplifier.
Okay.
Like in the simulation assignment. And how should I choose the value of R1? Should it be very high or should it be very low? Okay.
Okay, so generally those R1, R2 values are not in your control to the first order, they are given. But in general, yeah, so you wouldn't want them to be such that they are loading your OTA.
Exactly. That's why I was thinking like, I was thinking this way, if the value of R1 and R2 is small, in that case, the error current, because of the steady state error, there will be an error current.
Yeah.
Okay. So that error current would be really high.
That drops the DC gain essentially. That drops the DC. If it loads, it drops the DC gain over the overall system. So that's why you don't want it.
But if we choose the value of R1 and R2 high, in that case, we will have the small gap error current. And that small error current basically means that the steady state error is small. But
that doesn't mean that you can go till very high value because there is a capacitance at the input of the OTA also. So that increases, that will cause a low frequency pole. If
at the input, sir.
Yeah. Okay. The LFS will have a low frequency pole, right? So if you have, this question is, let's say I have a system like this. Inverting, non-inverting doesn't matter.
Yeah.
So how should I decide this R1, R2? So, I mean, ideally this also has a GDS. Ideally, you don't want this R1, R2 to be much smaller than GDS. I mean, 1 over GDS, because otherwise this will load, right? This will drop the DC gain. So you want the DC gain to be generally set by GM by GDS, not the feedback network. So generally, your R1 by R2 R1 and R2 should not be very low, but that doesn't mean that R1 and R2 should be very high, because ultimately you have a capacitance here. You have anyway a capacitance there. So if R1, R2 is very high, this pole associated will be a very low frequency pole. And you have already from the last few classes, you know what happens if you have multiple low frequency poles. So that essentially sometimes limits what is the value of R1 and R2 that you can take.
So basically, a high impedance node is a very crucial factor in negative feedback system, right?
I don't understand the meaning of that.
So because of the high impedance at that node, and because of that parasitic capacitor, the
pole
is moving to low frequency.
Okay, yeah. So yeah, true. So if you, in the open loop case, so when you open the loop, so essentially you do this. So you apply a test voltage here, right? So this is V test and this is V return. This anyway is a high impedance node, and if this becomes high impedance node also, then you have two low frequency poles, right? So that can cause an issue. Okay.
Any possibility of low frequency zero?
There are, I mean, you can have low frequency zeros, but I don't think we'll have time to get into that. Today's lecture, there will be an involvement of a zero, then we can take into account something like that. But generally, zeros don't come for free. For example, you might say that I can always cancel out the effect of a pole by adding a zero in the transfer function. If we could do that very well, very good, we can do that. But in general, what you will see, if you take more and more circuit level courses, or you get yourself involved into more circuit level stuff, so you will see that zeros are almost always associated with another pole. You cannot have a free zero, mostly. Put a zero, there will be another pole also. And the question then boils down to, where is that extra pole located? If it's also a low frequency pole, then putting that zero doesn't make any sense. Okay, fine. So now we did, in the last class, we did essentially hardly any circuits, but we drew multiple plots, Brody and Nyquist, and try to figure out what the relative location of the poles with respect to P1, P2, omega U loop, and so on, in order to get something stable, right? By stable, we mean not outright instability. By stable, I mean that you have a stable step response which doesn't ring and all, right? So we are essentially trying to figure out what are the locations of the poles with respect to omega u loop or the relative separation of the poles, so that your system doesn't rings, but it settles without ringing. So that essentially was the theme of the last couple of lectures. And quick recap of the outcome of those analyses was the fact that if we consider an all-pole system, then, and if we consider, let's say, a second order system, then if we have two poles, let me call this one P1, let me call this one P2. My omega u loop is at a certain location between P1 and P2. What is the relation between P2 and omega u loop to get critically damped condition? Yeah. So essentially for critically damped, for zeta equal to 1 in closed loop, obviously, then this is L of S prol, right? So for L of S, your P2 has to be equal to 4 times omega u loop. Okay. So this is for this is particular to your second order system. But then we said that we will extend it to any order system. But in any higher order system, the concept of zeta is not there. But how do I match the response of a second order system with any higher order system? Then we said that we'll introduce a concept of phase margin, right? And phase margin was essentially the phase lag that you have, excess phase lag that you have at omega u loop. Okay. So if you had, this is 0, this is angle. In a second order system, this maximum phase that you get is minus pi at omega u loop. In a first order system, you would have gotten minus pi by 2, but here you will get something which is minus here. So you will get something on top of minus pi by 2. And then we said that we have, in the Nyquist plot, we have to steer clear of this -1, 0 point. That is, whenever you are cutting the UGB, you will have to be away from the 180-degree phase shift, right? So how far you are away in terms of angle, this essentially is the phase margin. Then we said that if systems having identical phase margins behave identically, that was the hypothesis that we made, which strictly is not true, but this is practically something that we see is acceptable. So since that is the case, then we say that we will ensure that systems with any phase margin, any system with identical phase margin behave identically. So that was the hypothesis that we did. And what was the phase margin for step response? What was the phase margin for step response without any overshoot? Phase margin requirement for no overshoot?
74 degrees.
Right, 74 degrees. Right. So then essentially we essentially said that if you have like n poles, one of the poles obviously will be at a low frequency. That will give you pi by 2. This pi by 2 is this pi by 2 phase lag will anyways be there, that you cannot really, that essentially gives you that integrator type response. And that additional 16 degree phase lag has to be given by all the n minus one other poles. So which means that if you have like more number of poles, each pole can give you smaller and smaller phase lag, and which means that they have to be at higher and higher frequency, because this is phase lag at omega u loop. If your excess other poles are closer to omega u loop, they will give you more and more phase lag. So that essentially was, in a nutshell, is the conclusion of the last 2 or 3 lectures. So now since this is a circuit design course, we have to see that how does all this thing tie with our regular circuits that we have been doing. Okay. So before I think 4 lectures back, before we went into all this Nyquist plot and stability analysis business, the circuits that we were getting concerned about were these, right? So this is GM1, GM2. So V0 over VE would have been our L of S. And this we can express in the form of A0 by plus S by P1 and plus S by P2, where A0 is, what is A0? GM1, GM2 by GDS1, GDS2 by 1 plus S by P1. What is P1? GDS1 by C1, CO1. GDS2 by CO2. And if we assume that GDS1, this P1 and P2 are close by, right? If we assume P1 and P2 are close by, let's say this is P1, let's say this is P2. So you essentially get this. This is minus 40 dB per decade. So now I don't have to tell you that this is clearly not what we want, because ultimately what we want is the relative pole locations to be separated, right? So in this case, what we want is to separate the poles P1 and P2 out, so that around omega U loop, you have 20 dB per decade roll-off. So now we haven't yet explored, or you don't even know if we can push poles out, right, without compromising DC gain, which essentially means that we probably will have to go the other way, that is push the P1 or P2 at lower frequency. And how do you push any pole at lower frequency? Easy thing to do is to just put an additional capacitor. I mean, you can also say that I will reduce the DC gain, yes, but it's, I mean, sometimes it's easier to, sorry, I will increase the DC gain, but assuming your DC gain is fixed because of the overall steady state error response and all. So what you want to do is to, the only handle that you have is put an additional capacitor. So if I put an additional capacitor at this node V1, right? If I put an additional capacitor C, okay, and let's assume the total capacitance is C, that is the parasitic capacitance, and the additional capacitance is C, then our this entire thing will get shifted to my DC gain on change. So let's assume my new P1 is here, and this goes something like this, and then it goes like this, right? So this is my new omega U loop. Okay. So now, given that what we know, tell me what is P1, new P1, P1N. Yeah, P1N is GDS1 by C, right? So this is the P1N. By the way, I mean, even though I am writing these poles as a positive quantity, I mean, at the back of your head, you should understand that all these poles are on the left half plane, right? Because otherwise it becomes an unstable system. Okay, so if that is the case, what is omega U loop? How will you figure out what is omega U loop? Yeah, so what will be L of S if I consider this line segment? A naught by 1 plus S by P1 will be S by P1. times 1, right? Because 1 plus S by P2 is high frequency. So in this case, what is L of S? Then if I replace all the terms, this becomes GM1, GM2 by GDS1, GDS2 times P1 by S, where P1 is C by GDS1 by C, right? GDS1 by C times S, right? So this effectively becomes GM1, GM2 by GDS2 C S. Okay, so your omega U loop has to be, if things are working as you expect, then your omega U loop has to be how much? Okay, so still, I mean, we have only figured out what is omega U loop. We haven't yet figured out where the pole P2 is. I mean, with respect to P2, where is this omega U loop, right? Because ultimately we have one handle. We have this handle of C. If we figure that this omega U loop is not, if P2 is not at a sufficiently high frequency, then I have to pull omega U loop to lower frequency, which means I have to increase C. So the whole endeavor is to figure out what is the optimum value of C. Okay. So for that, I have to figure out the relation between P2 and omega U loop also. So in this particular case, what is the relation? P2 is 4 times omega U loop. So P2 is 4 times omega U loop for critically damped condition. By the way, this P2 equal to 4 times omega U loop is for critically damped condition for 2-pole system, right? It's not like for any pole system this relation holds. For any pole system, the relation that holds is phase margin. Okay, this is for 2-pole and no zeros. I didn't understand. Correct. Right. So for if you have more number of poles than P2, then obviously this P2 has to be farther away, which means this factor of 4 will increase. Right. It will be maybe 5, 6, 10. I don't know. Depends on how many poles you have. Okay. So now, which essentially means that what is the relation? P2 is GDS2 by C2. And this becomes 4 times G. Okay, so the constraint on C becomes C has to be 4 times GM1, GM2 by GDS2 squared times C2. And if you assume that GM1 by GDS1, GM2 by GDS2 are of the same order, then this term is essentially the equivalent to the DC gain of the two-stage contraption, right? The DC loop gain, which essentially means that, as you see, if you are shooting for very high DC loop gain, you want a very large value of capacitance just to compensate, right? If this is, especially if let's say this is some output capacitance, I don't know, maybe 1 picofarad, and you are planning to stabilize it using the method that we just saw, and let's say your DC gain is 60 dB, 1000, which means this C has to be like 1000 picofarad, 1 nanofarad, and 1 nanofarad capacitance in an IC is almost unrealizable. You can probably realize about 10 picofarads very easily. Sometimes we go to 100 if it's absolutely necessary, but 1 nanofarad is almost out of question. Okay, so that you see, I mean, which essentially means that this type of compensation has some limitations. Okay. Any questions? Okay, so now the question becomes, how do I mean, this essentially, okay, so why is this causing a problem? This is causing a problem because we initially we use identical types of stages. That is, we only had a single stage GM. So then we said we want to better it. then we will use 2 of those stages because we only had 1. So you basically had used, we repeated what we had. Then what we ended up with is poles at almost similar locations. Then we said that we cannot move the poles out. Then why don't we do the other thing, that move one of the poles in? Okay. So this, I mean, that gave rise to this issue. And the issue that one of the reasons this ended up being an issue is because we have not been able to move one of the poles out. We are only moving one pole in. And then this is probably not an issue if you are doing a board level design. Okay, if you are wiring up your circuit in a breadboard, or you are doing a PCB design, then this also is probably not an issue, because you can, I mean, the size of a 1 nanofarad capacitor and the size of a 10 nanofarad capacitor is almost identical on a board. Okay, because it comes with a package and we just plug it in. But it's not the case in an IC. And in IC, the IC real estate is very expensive. So you would like to figure out which one is the most area consuming component, and you would like to reduce it. And as it turns out, in most analog circuits, all these compensation capacitances, and if you use inductances for some reason, they are the most area consuming parts. The transistors essentially come for free, because, I mean, this aspect ratio is so small, they hardly take up any area unless you are trying to design a power amplifier, you are driving 1 watt power and all, then the transistor size becomes large, I mean, appreciably large. Otherwise, it's almost always these compensation capacitances take up most of the area, which means there is enough incentive to figure out how can I reduce this compensation capacitance. Now, one way to do that is to recognize the fact that, I mean, if I use something like, have you heard of this thing called Miller effect? Okay. So what is a Miller effect? In a Miller effect, what we do is we say that, so when we have a capacitance, let's say I have a grounded capacitance, what is setting up this capacitance? We essentially are trying, if I just say that, if I apply a voltage here, the current that is flowing through this is SC times V, right? Since this current that is flowing through this is SC times V, and the effective capacitance that I am seeing is C. So if I can increase this current by, let's say, a factor of whatever, A. So if I can increase this current by, so I have a capacitance inside a box. I don't know what's inside the box. And I apply V, and I observe the current that is going in is SC times V times A. Then looking in, I would have the feeling that I am driving a capacitance of the size of C times A, right? So, I mean, how I am doing it, it's up to me, but to the user, it will feel that you are driving a large capacitance. So now we know that this entire current thing, right? So when everything is a loop, it's not as if your current goes and stays. So it has to come back, right? So this is a loop. Okay. So in this loop, in this particular loop, you can assume that one of the terminals of the capacitor is shorted. So somehow, if I can increase this voltage, if I can induce a voltage of minus V times A, right? Then the current that will get drawn through this capacitor will be SC times 1 plus A times V. Right? Because now the voltage difference between the plates of the capacitor is 1 plus A times V, which means that the current through the capacitor will be SC times 1 plus A times V. So if we can do that, it will seem to the user sitting outside the box that you are driving a capacitor which is of the size whose value is C times 1 plus A. And if A is large enough, it seems like C times A. Okay. Note that what is the good thing about this? It's a good thing about this is the fact that you can get away, you can effectively take a small capacitor and make it mimic like a large capacitor. If A is 1000 and if your capacitor is like 1 pico, then it seems like you are driving a 1 nanofarad capacitance. So obviously now you see that this type of contraption has a lot of incentive in IC design because I can effectively reduce the capacitance area. Okay, so now how do I now the problem boils down to a different, I mean, the challenge is now at a different place. So what is the challenge? The challenge is how do I generate this minus V times A? So if you had an ideal voltage control voltage source, then I can simply say that I will do this, and that will be my V times A, and this is essentially your Miller effect, right? You are amplifying the effective capacitance by the factor of the gain of the amplifier. So now, I mean, last class today, I'm sure you understand the issues with this because we don't have a voltage control voltage source. Okay, so we never have a voltage control voltage source. I mean, even if you take infinite number of classes, you will never have an ideal voltage control voltage source. You will only have better and better and better, or worse, I mean, something, right? So yes.
Sir, in this circuit, as you said that another terminal of the capacitor should be grounded in order to close the loop.
Right.
So in this case, if we connect that output another terminal where this minus V times A is there to the ground, then that voltage will be essentially 0, right?
I didn't understand.
Like,
which voltage will be 0?
How do you close that loop? This circuit.
This loop?
No, this whole circuit.
No, the second one you are saying right hand. Okay, so okay, now tell me, I mean, what is this A? How do you make that A?
Using the amplifier.
Using an amplifier. So current goes inside the amplifier. Amplifier has grounds, right?
Achha, internal ground.
Yeah, so they are closed. Okay, so now we don't have an amplifier, but we have a poor man's amplifier, that is this VCCS, right? So, and what are we now saying? What we are saying is, instead of using this, what we don't have, let's use what we have and then see what happens. So what we have this GM1, and we have this GM2. C1, GDS1. We were initially trying to put a large capacitance here, right? We are initially trying to put a large capacitance here, and we're trying to mitigate, I mean, trying to move one of the poles away. Now we are saying that, hey, I mean, looks like this is a poor man's VCVS. So why don't I use the DC gain of this and try to amplify a capacitor, right? So the idea is I will put a capacitance here, and if everything goes according to plan, the looking in impedance capacitance will be how much? 1 plus the gain of the second stage, right? So ideally it should be 1 plus the DC gain of the second stage. That's what we expect, right? So ideally this should be, looking in capacitance should be 1 plus GM2 by GDS2 times C, sorry, GM2 times, yeah, this one, right? So this should be ideally the case, but I think one of you pointed out that effectively it should be, I mean, there is no reason for us to assume that it will be this, because ultimately that what is the gain of this GM2? It's not a frequency independent gain, right? If I take into account the fact that there is a C2 there, so this capacitance will, this impedance will not look fully like a capacitance. It will look like some contraption which has S terms, SS, maybe something else associated with it. So this clearly will not solve our issue completely, but it might help us in some way. Maybe at some frequency range, it acts as a capacitance. And that clearly you can appreciate now, because at frequency ranges where I can neglect C2, right? At frequency ranges where I can neglect C2, this looking in impedance into wherever I have shown, it would seem like my capacitance is 1 plus GM2 by GDS2, because C2 is not coming into picture. In those frequency ranges, it can still act as a Miller capacitance. Okay. Yes.
The first stage of this right? So we're putting the signs of the input error voltage signs here putting on.
This one?
No, no. Yeah. So
Oh, okay. Yeah, I mean, so this for the purpose of this analysis, it really doesn't matter because
as long as you're considering V to be positive.
yeah, so it's V naught over VI. I mean V now. I mean, it might as well be because it's negative. That way, you will get a negative something. But ultimately, when you will be closing the loop, you will be ensuring that it's closed in the right way, right? So that way, it should be fine.
Sir,
Yes.
in this circuit, we have considered the ideal voltage from the voltage source.
In the previous circuit, yeah.
With a gain of -6.
Right.
But sir, this is not a voltage control.
Exactly. Correct.
It has a high output impedance.
Correct.
But even if with the low, if you consider low frequency,
Yeah.
in that case, capacitor behave like open circuit, no feedback. We
Correct.
cannot say that the output impedance is.
I'm not
1.3.
looking at zero frequency. At zero frequency, definitely there is no feedback.
No feedback.
Yeah. But at frequencies which is non-zero, then one can argue that there is a capacitance that you can see. There is a feedback.
At that frequency, it is behave like a voltage control voltage.
Well, we'll see. We'll see, right? So this is, I mean, we haven't yet figured out what it is. This is the expectation, right? So this is the expectation. So you design something. It's not as if you have an ideal circuit on your paper and you design. You have some knowledge. You try to figure out how can I better it by using that knowledge. So its progress is always incremental steps, right? So then you probably found that this is something that will not be able to use or maybe you will be able to use, right? So that's why research takes time. You come up with n number of ideas out of which n-1 doesn't work. Then one works. Okay. So, I mean, the way we structured this course, because we have only like 13 weeks, is only to mostly tell you what works. Right? But ultimately, if you go into research, you will have, it's quite the other way around. At least in this flavor, in this way, I try to structure, I at least try to lead you through the direction, but it's never a straight road.
Sir,
yes.
it's usually always trying to pull towards the left.
Yeah.
But is there any other going on because working?
You will see, right? In this case itself, you'll see what happens. So I mean, with the existing knowledge that we have, it seems like, I mean, as you pointed out, this is supposed to be a voltage controlled voltage source. This is a voltage controlled current source. Here we assume in voltage controlled voltage source, ideally output impedance has to be 0. Here it's not. So a lot of things are going on. So how can we figure out what actually is happening, right? So what we'll then, I mean, if we don't know what exactly actually is happening and things become complicated, just do a brute force analysis and then see whether we can break that down or not. Okay, so let's do a brute force. So let's say this is V1, this is V0. Okay, so I am trying to figure out what is V0 over VE. Now it might seem quite messy, but if we do it in a systematic manner, then you'll see that it's not that messy. So what I'll do is I'll try to write the KCL at both nodes V1 and V0. Okay, so at V1, KCL boils down to GMs times VE is equal to GDS1 plus SC1 times V1. Follow along. If you see that something is wrong, just give a shout. Plus, this is the current that is going out. So GDS1 plus SC1 plus SC V1 minus SC times V0. Okay. And at KCL at V0 will lead to, there is nothing that is being fed directly. So this is 0 is equal to, so you understand, I'm trying to get it in a form so that I can get a matrix done, right? So that something is V1 here, something is V0 here. So I'll be able to do a matrix inversion. That's the whole idea. So if I concentrate on V0, at V0, what is connected? You have GDS2. C2 plus SC. Not. And at the effect of V0 on V1 is essentially in terms of KCL will be one is I'm pulling current out, so this will be GM2 minus SC. Right?
So, how can you radically write that AC term over there? After rearranging, we can write this way.
Yeah.
Looking at the node GDS2 plus SC2, it's okay. Then
Yeah. No, so what is this current? This current is V1 minus V0 SC. Right? So you allocate.
Achha. We're just thinking and
Yeah,
you
yeah.
have to add that term minus AC over and plus AC over.
Correct. Yeah.
Okay.
So, so now we have this form. So we can write it in this form, in the matrix form. So this becomes GDS1 plus S C1 plus C minus SC. Okay, so how many of you remember Kramer's rule? So, which means that I can find, so I can say your V0 will be determinant of this. And in the numerator, I'll be replacing this stuff in the second column. So this becomes, this is something here, this is something here, this is GMVE, GM1VE, and GM2 minus SC, and here it will have Z with 0, right? So it doesn't matter what is here, because ultimately determinant will go to 0. So now let's do the brute force. So this becomes and in the numerator we get okay. So your V0 over VE becomes minus GM1. Now you already see there is a 0. So in the previous L of S there was no 0. Now you see there is a 0. But something even more interesting is happening in the denominator. So let's take the S squared terms together. So we'll have C1 C plus C2 C plus C1 C2 plus C squared, and you have minus C squared here. So 1 C squared will get cancelled, plus S will be GM2C plus, right, this next line. Right? Did I miss anything? Looks right, right? Okay, fine. So this seems to be a monstrous of an equation to analyze for poles, which actually it is, because how do you do a second order system? You do this minus b plus minus b square 4a and blah blah, right? So in general, if you are planning to do a general analysis of this, it becomes slightly messy, quite messy, but we don't have to do general analysis because we are not trying to figure out a general solution. We are trying to figure out a solution for a case where the poles are far apart, right? So if we assume that poles are far apart, right? If we assume poles are far apart, and if you say that this is a quadratic equation, as square plus bs plus c, and I have to figure out the roots, right? So assuming poles are far apart, how can you approximate? You have P1, this is true, right? P1 plus P2 is minus B by A, and P1, P2 is C by A or C by B? Okay, so now, yeah, this is true, but if you assume that P1 and P2 are far apart, and if you assume that P2 is more than P1, right? So if P2 is much more than P1, then your P2 effectively becomes minus B by A, right, from here. Then P1 becomes minus C by B. Okay, so this kind of narrows down the difficulty a bit more. I mean, rather narrows down the problem a bit more, and seems like we can, we at least have a light at the end of this tunnel, right? So then let's, we know what is A, B, C here in the sense of the quadratics. So let's do P1. Okay, so what will be P1 in terms of P1 is minus C by B. So C is easy, C GDS1, GDS2. The B is the other term, right? So this is correct. Okay. So this becomes so I will collect the terms which have C together, right? I mean C as in this capacitance together, because ultimately we are trying to amplify that capacitance, right? So that will probably make some sense. So let's do that. So this becomes C times GM2 plus GDS2 plus GDS1 plus, what do you have? This should not be here, right? Plus C1 GDS2 and C2 GDS1, right? Okay. So what I'll do, I will divide. So still it looks slightly messy, but ultimately, see, I mean, what we are trying to get, this capacitance to look like a larger capacitance, and that is of the order of GM2 by GDS2. Right? There has to be something in order for us to get an appreciation of what's happening. We have to express this, massage these terms in such a way that I get something like C times GM2 by GDS2. So what I'll do, I'll divide it, the numerator and denominator, by GDS2. Okay, so this becomes GDS1 by C times plus 1 plus, yeah, plus GDS1 by GDS2. Right? Okay, so assuming there is no algebraic mistakes, this is my P1. Okay, so now what is P? I mean, now let's go back and see if this makes some sense. So if this looks like C times 1 plus GM2 by GDS2, right? What would you expect the pole location associated with this node to be?
GDS1 divided by
GDS1 divided by
C1 plus
C1 plus that term, right? So you see that we kind of are getting that, right? So if I take this one out, so this becomes C times GDS1 by GDS2 again. So this, what you get in the denominator is the effective capacitance, and the stuff that you are getting on the numerator is the effective conductance of that number, right? So now you have some additional term also, which is expected because we have done so many gross oversimplification. This is not a Miller capacitance. I mean, this is not a voltage control voltage source, the second stage. So you expect that there will be some error with respect to if we had voltage control voltage source. Now, the only thing is that the error is dominant or the error is negligible. If the error is negligible, we can say that we can still use this contraption. Okay, so what do you think? Is that in the denominator, the stuff that we are neglecting, is it dominant or this is non-dominant?
C2 and C are small, basically.
C2 or C are same order. Let's assume all the capacitance are of the same order.
And GDS and GDS1, GDS2 are
Same order.
So small amount of capacitance getting added.
Yeah, but the major term is GM2 by GDS2. GM2 by GDS2 is large, which means that will dominate, right? So which essentially means that seems like we can still use it as a capacitor amplifying device. Okay, even though this is not a voltage controlled voltage source. So this is as far as P1 is concerned. Now, but what happens to P2? Is P2 getting affected? So this seems like I can move P1 down by using this, but let's see what is affecting with P2. So what is P2? Minus C by B, right? So minus B by A, sorry, yeah, minus B by A. So this entire stuff will go to the top, right? And what is A? A is this stuff. C1C plus C2C plus C1C2. Okay. So I will do some algebra here, which will initially probably will not make sense to you, but hopefully in a couple of minutes. So what I will do is I will divide the numerator and the denominator by C1C. Okay. Don't ask me why right now. Just hold on. So if I divide the numerator and the denominator by not C1C by C1 plus C. So this becomes C1C by C1 plus C. Okay. And something is wrong. So this I can express as
C times C1 plus C2.
this one and this one. Is this correct in terms of the signs, in terms of dimensions? Yeah, in terms of dimensions, it's correct. In terms of dimensions, it's correct. Okay. So if I take C2 common here, so this becomes C plus C1, right? Okay. So now let's divide by C plus C1. So if I divide by C plus C1, you get C2 plus C1 by C plus C1. And in the numerator, I get Gm2 C by C plus C1 plus, if I take these two GDS2 together, right? This GDS2 and this GDS2 together, I have C plus C1 as their coefficient. So this becomes GDS2 plus I get GDS1 again together. So this becomes C plus C2 by C plus C1. Okay. Okay, fine. So now let's look into the second stage physically and see whether this stuff makes sense or not. Okay, so let's do the easier one, the denominator. Okay, so your pole, if it's a real pole, and if you can split up your higher order system into small blocks of first order systems, then I can say that a pole is essentially inverse of the time constant. Right? If it's a first order system, a pole is inverse of time constant. Right? So a time constant is what? Some conductance by some capacitance. So if I look into this node V naught, okay. So what is the capacitance that I am looking at? You only consider capacitance. You desensitize GDSs and everything. If you only consider capacitance, what are you supposed to get?
C2 plus the Miller capacitance because of that.
Will you get Miller capacitance? That's the question.
So we will get, but that will be very small, right? C by 1 plus A.
Why? No. Don't get into that. Look into the circuit and tell me. Don't get into Miller and what you remembered. So it looks like that I have a full capacitance C2 and something C and C1 in series. Isn't it? So that's what you see here. Okay. So looking at the output node, you essentially see one capacitance C2 and two capacitances C and C1 in series. So from looking at the picture also, it seems like something like this exists. Some contraption like that exists. Make sense? Yes.
We will not be able to apply that Miller capacitance over here because we are looking at the output node, right?
Yeah.
Whenever we apply the input node, in that case, at the input we get some extra capacity and
right.
the output node.
Yeah. So you don't have Miller effect essentially here, right? So essentially, how do you figure out what a capacitance? I mean, let's say you have a circuit jumbled together, and I tell you there is a capacitance associated with it. How do you actually simulate and figure it out? If you're not given the option of looking into it, you only have the access to the terminals. How will you simulate and figure whether you have a capacitance?
See the current and voltages across the terminals.
And with respect to what simulation will you do, or what type of experiment will you do?
Like we will see over the frequency.
We will see over the frequency, right? So it's essentially when you say that you will see over the frequency, and you'll be trying to look. You try to estimate if there is a 1 over S kind of slope at over some frequency range, and the slope will essentially have the information of the capacitance, right? So which essentially means that you are saying that if such a region exists, the conductances don't play a part there. It's purely capacitance, right? So which means that in your analysis, you can then say, I will null all the conductances that I have. If I null all conductances, this goes, this goes, this goes, right? So what do you end up with? You ended up with C2 and in parallel with C1 and C. So that's what you get.
So why we are nulling that conductance?
So that's what the analogy I gave, right? So if you have, let's say you are looking into the current voltage over frequency. You're trying to figure out the Z over frequency. So you might have slopes like this, then something like this. Then you say that over certain frequency range, it looks like capacitive. So when you say over certain frequency range, it looks like capacitive, you are inherently saying that there is no conductance associated with it, nothing else associated with it. So in your analysis, if you have to do the same analysis, I'll get rid of all the conductances. Whatever I am left with, if there is a capacitance, that is my effective capacitance. Okay. So if you are convinced with the capacitance part, I'll go to the numerator part where where the most important, most interesting stuffs are happening, even better than the traditional Miller cap. Right. Yeah. So in that, that's a good question. So what her question is basically the fact that it looks like we have a control source. If the control source itself is affecting the capacitance that we are trying to figure out, then we cannot neglect. So that's what was happening when we are looking from the input side, isn't it? From the input side, if when we were trying to figure out what is the capacitance looking in here, we cannot really null this GM2 because the output voltage is getting controlled by the input, and that's what it's getting us the Miller cap. So again, these type of approximations don't always hold. Okay. So in some cases they do, in some cases they don't. But if you have control sources, you'll have to be slightly careful. That's all I mean, right? So looking at the hindsight, this seems to hold, but in some cases they might also not hold. Okay. So the reason I massage the equation in this format is to at least give you a feel if I can decouple what am I trying to do? I am trying to essentially decouple two parts of the circuit. It's a circuit where the first stage and the second stage are combined together. They're talking to each other. So having trying to figure out where the poles locations are when multiple stages are combined is slightly difficult. If I can say that these are equivalent to two first order systems cascaded together, then I can easily figure out what the pole locations are. Right? So that's the motivation. So we should be able to look at a circuit and figure out what should I do to the components to move the poles in the directions I want. And we are comfortable with first order RC networks. So we are trying to figure out how can I analyze my circuit in such a way that I break it down into time constants. If I can break it down into time constants, then it's easier for me to manipulate the locations. So that's essentially the motivation. So in a time constant, you have a capacitance, you have a conductance. So you're trying to figure out what is the conductance, then we'll see what is the, so we try to figure out what is the capacitance, then we'll see what is the conductance. But that is a very good question. Okay, so now let's move to the numerator. In numerator, what do you think? Okay, the easiest term is GDS2, directly connected V0. So that should appear. But what is this extra term, GM2 C by C plus C1? And one might argue that this term is dominant because if C, C1, everything are of the same similar order, GM2 is much higher than GDS, which means that this will be the dominant term, in fact, right? So what is happening with this? So what is this?
Is that because of the current splitting?
What do you mean by current splitting?
Because there is a capacitor C2 over here and there is a path another one C and C1.
Yeah, it's not a current splitting per se, but there is a feedback. There's a feedback around GM2, right? So see this, what does this seem like? This seems like if you have a GM2, if you have a conductance GM, it seems like if you had a conductance GM and you put it in diode connected node or unity gain feedback, what is the conductance that you will get? Let's say you have a transconductance GM2 and you put it in unity gain feedback. What is the conductance that you will get looking at the output? You will get 1 over G. 1 over G is the impedance. The conductance that you will get is GM. You will get GM2. But looks like you are not getting full GM2, but there is a fraction. There's a voltage division is happening, which means maybe the entire test voltage is not appearing at the input, but some fraction of it is appearing. So now if I look in, if I apply a test voltage here, if I apply, let's say a test voltage here, and try to see what is the current that is drawn by GM2, what will I see? If this is V test, approximately what voltage will appear over here?
Times C1 divided by C divided by C1.
V test times C divided by C1 plus C. Correct? So the current that you will draw will be GM2 times C by C plus C1 times V test. Okay, so that essentially is telling you that looks like there is a, because of this GM2 in feedback, there is a conductance which is equivalent to GM2 times C by C plus C1. So that's what you are getting here. And again, there will be this extra pesky terms because a lot of approximations, but those pesky terms are not dominant. Okay, makes sense? So now note that as I alluded to 5 minutes back, this term will be the dominant one. Okay, so if that is the dominant term, what is the effective location of the pole now? And let's assume that this C2 is, I mean, you can have this entire thing in the denominator, but let's say that C1 by C plus C1 is series combination of C1 is less than C2. So I'll approximate the denominator as C2. Okay, so if that is the case, what do you get? Where is the pole? Minus GM2 C by C plus C1 times 1 by C2. Okay, so can you comment when you didn't have this pole with this capacitance across? So what was the P2 old? GDS2 by C2. So now can you comment on the relative locations of the poles between the old and the new configurations, P2? Right, so the P2 and divided by P2 old is what? Is approximately equal to basically GM2 by GDS2 times C by C plus C1. Okay, so it seems like I have not only been able to get a Miller capacitance and push the pole, low frequency pole at a lower frequency, I've been able to push the P2 pole at even higher frequency also. Right? It gives me two benefits.
C and C1 are the same order, right?
Yeah, I can assume C and C1 are the same order. I not even assume that. You can also assume that C is higher than C1. Because C is in your control. Right? You can put C to be much more than C1. So in that case, it P2 over P old is essentially one factor of the gain.
So main factor is coming from that term, GM2 divided by
Correct.
GDS2.
Yes. So essentially, to quickly recap, what is this Miller compensation across the second stage helping us do? It's not only helping us to move, it's helping us to split the poles, not only by moving one of the poles to lower frequency, it is also moving the second pole to higher frequency, right? So it's giving us double benefit. And very seldom you get a situation where you do one thing and you get two benefits. So almost there is a trade-off. You trade off one with another. Okay, so So if that is the case, now quickly, if I have to sketch this new L of S of the Miller compensated op amp, ideally, this is what we are looking for. So where is P1? Approximately expected P1, which is close to what we got, is GDS1 by gain of second stage times C, right? So this is approximately 1 plus, let's say, A2 times C. What is P2? This is GM2 times C by C plus C1 by C2, approximately. And if you don't want to make that approximation, you can still do this. Okay. So now the question is, I mean, before we did all these things, P1 and P2 were lying somewhere close by, and you were having this, right? So this was the old situation. So now we have been able to split the poles apart. Okay. So now, how do I figure out what is my omega U loop? Do the same thing,
From P1 itself.
right? So I can easily figure out from P1, and omega U loop will be N0 times P1 effectively, right? Because I neglect the second pole. So omega U loop. So again, this is basically A0 by 1 plus S by P1, 1 plus S by P2. This is dominant, and this is effectively equal to 1. So at the frequency where it goes to 1, S goes to 1 is A0 times P1, which is GM1, GM2 by GDS1, GDS2 times P1 is GDS1 by 1 plus A2 is A2, which is GM2 times by GDS2 times C. Okay. This goes, and you are left with GM1 by C, right? So this is then GM1 by C. Okay, so does this seem familiar, GM1 by C? So this seems like we have the omega U loop is similar to that of this, right? The first order system omega U loop where I had a GM1 loaded with a capacitance. I mean, you might have GDS and all also, but unity gain frequency doesn't change. Okay. So now this looks like this is one side is a grounded capacitor. You are driving a GM with a grounded capacitance, right? And then you get GM1 by C to be the unity gain frequency. So where is the grounded capacitance here? But looks like a C is grounded, right? If GM1 by C has to be omega U loop, GM1 I clearly see, but the compensation capacitor C seems to be grounded. It has two terminals. One of the terminals should be grounded. That's why we get GM1 by C, right? Where do you see a ground? Do you see ground? Do you see a virtual ground? Where is the virtual ground? The virtual ground is essentially, I mean, ideally the virtual ground should be this. It will never be a perfect virtual ground because GM2 doesn't have infinite gain. You have feedback around GM2, but it acts similar to a virtual ground. If this is a virtual ground, what is V0? If I assume that that is a virtual ground, the current that is flowing out through GM1 is GM1 times V, which flows into the virtual ground. If it flows into the virtual ground, what will V0 be? If this flows into the virtual ground, which means it flows to the capacitance, what will V0 be?
This times the 1 by SC.
Right, so it will be minus GM1 PE by SC. Right? From there, you can directly see why we are getting this GM1 by C to be the unity gain frequency. it's an effect of this intermediate node P1 being virtual ground around the frequency of interest, right? Around omega U loop. Clearly, this is not virtual ground at very low frequency because you don't have any feedback around GM2. You have only capacitance, which is open. So at low frequencies, you do not have any feedback, but around these frequencies, around this range, you have feedback, right? Because, I mean, no feedback means what? Your L of S is without any capacitance, right? Because this capacitance is open, L of S is basically GM1 by GDS1 times GM2 by GDS2. No capacitance anywhere. This is the frequency domain, or the region of frequency, range of frequency, where there is no feedback around GM2. But when you start getting feedback, if you start increasing the frequency, and moment you start whenever you are starting to see the effect of Miller capacitance, you hit the pole, you hit P1, right? So which means the capacitance C starts to come into picture around that frequency, around P1, and which means the feedback around GM2 also has started to kick in. Since the feedback around GM2 has started to kick in, which means that you are starting to get virtual ground kind of feel around GM2. Okay, so if this is virtual ground, your V0 effectively between P1 to P2 can be expressed as this, which means that your omega U loop will be GM1 by C. Okay. So now so just to tie things together, you also have a zero. What is the location of the zero? Where did I go? What is the location of the zero from here? It's GM2 by C, right? And note that this is a right-hand side zero. It's not a left-hand side zero. So you have a zero. Which is GM2 by C. This is plus, which means that if I sketch the loop gain plot again, so you'll have P1, you have P2, then you'll have a zero. But in the phasor plot, if I draw the angle, this is mod L, this is angle L. So you start from 0, then you go here, you hit another pole, and this 0 will cause phase lead or phase lag? Phase lag, right? So had it been only a second order system, at infinite frequency, your phase would have settled at -180, but now it will go to -270, right? So it will go to -270. Which essentially means that if the 0 is somewhere nearby, right? If the 0 is somewhere nearby omega U loop, it will have an extra phase lag at omega U loop without the effect of 0. I mean, had the 0 not been there, right? So assuming that 0 is above omega U loop, right? So assuming Z is at greater than omega U loop, what will be the phase margin? What will be the excess phase rather? Angle at omega U loop. Due to P1, it will be -π/2. Then you will have extra because of P2. What will be that for P2? What will it be for P2? Tan inverse? Tell me the expression. Omega U loop by P2. If had it been a second order system, pure second order system, we would have stopped here, right? And said that this term should give me 14 degree, that extra 14 degree for critical damping. But we cannot stop here because we have a 0. So which means you will have minus extra tan inverse omega U loop by Z. So now the addition of these two should be 14 degree for critical damping. Okay, so this is one of the, I would say, minor drawbacks of Miller compensated op-amp. You were about to give everything for free, but you don't get, right? There is some extra phase lag because of 0, but still this is in your control, because if you keep GM2 to be high, so what was your omega U loop? The omega U loop was approximately GM1 by C. So if you keep this Z to be greater than omega U loop, which means this, you have to keep GM, if you want to keep Z to be greater than omega U loop, which means you are planning to keep what? You are trying to keep GM2 to be greater than GM1. And if you keep GM2 to be much greater than GM1, then the effect of 0 is not significant. Okay. So, and you'll be fine. Okay. So again, I mean, don't bother too much about Miller compensated op-amp that at this stage. Miller compensated op-amp itself requires few lectures to do full justice. I didn't want to end the course without you having the flavor of what multi-stage op-amp is and how do you compensate, at least a brief primer of that. If you want to get the main course, take 613. There it's all about multi-stage op-amps, different configuration, different types of feedback, how to stabilize it. But essentially what we wanted, the goal of this course was to essentially give you an idea of how do I make a system which is a battery, right? A voltage controlled voltage source using the transistors that we have. The transistors are voltage controlled current source. Then we saw that we can put transistors in feedback to reduce the output frequency, reduce the output impedance, because voltage controlled current sources do not have, did I say transistors are voltage controlled voltage source? Let me rephrase it. The transistors are voltage controlled current source, which has high output impedance. But we saw that if we put it in negative feedback, my output impedance can go down, but it doesn't go down sufficiently if I use only one stage. If I use two stages, it can go down even better, right? So then we said that if we have two stages, then we have problems of stability, and then we require some way of dealing with the stability. We use frequency compensation. Then we said that if you use frequency compensation in one way, if you just add a capacitance blindly, then it seems like you are reducing omega U loop also. You are reducing P1 to a much lower frequency, which naturally means that your omega U loop also reduces. Then we said that if there is, I mean, let's explore if there is some other way where we get away without putting a very large capacitance, or also if there is a benefit of putting pushing some pole at a higher frequency. Then if we saw that if we put a capacitance around a GM, around the voltage control current source, then it seems like it does both. It not only pushes one of the capacitance at lower frequencies, but it also pushes other capacitance at higher frequency. So it seems like this seems like a better option than the previous. And I mean, you should know that now everything, if you put in negative feedback, it would seem like a better voltage control voltage source. Not ideal one, but something that we can live with. Okay. So yeah, so with that, we come to the end of the course. Hopefully, you guys had a flavor of what circuit design is, and hopefully I didn't bump you off, so that when you guys are still a bit more excited about doing this as a career, right? Okay, thank you.